Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today we will continue our discussion on image transform. In the last class, we considered how a transformation in the discrete space can be expressed as a linear transformation. That is, there is a transformation matrix, and multiplying that transformation matrix with the input vector, you can get the transformed vector. And we have given examples of discrete Fourier transforms, also its generalized discrete Fourier transform. Then we have seen that how discrete Fourier transforms can be extended for defining trigonometric transformations like discrete cosine transforms and discrete sine transforms. There are various forms of discrete cosine transforms, discrete sine transforms that are possible, and we discussed some of them. And in particular, today we will be considering, we will start our discussions with a particular type of discrete cosine transform, which is mostly used in various applications of image processing. That is called type 2 discrete cosine transform. And you can you can find the transformation matrix of this type 2 discrete cosine transformations, where let me once again explain how this transformation matrix is defined. So, this is an element of the transformation matrix. It is expressed in terms of its corresponding row index and column index. So, K is the row index and N is the column index. So, the values of row and column index varies from 0 to n minus 1. So, which means this is a matrix of dimension n cross n. So, because of this variation, it is a dimension of n cross n, where the first row, the value of k will be equal to 0, and then n will vary from 0 to n minus 1, and in this way it proceeds. So, this element, if we set the values of k and n from this, as we proceed in constructing the matrix element, then we will get the actual functional values or real values for this case. So, this is the matrix form of representation of the discrete cosine transform of n order in discrete cosine transform. We say n point discrete cosine transform because this transformation is applied to an input vector of length n. And a notation we are using just for our convenience, so that in subsequent discussion we will be using this notation. You should also notice that there is a scaling term into the elements, and which is row dependent. So, the first row, which is k equal to 0, where the value of alpha k would be root over 1 by 2, and this n is not valid in this case, but there are transformation matrix, particularly type 1 density transformation matrix, where for the equivalent n point density, there you have to use n plus 1 point density, because the period is twice n. So, for equivalent period. So, there this definition is useful. And then for other cases, it is 1, which means that the scaling term for the first row is root over 1 by n. So, if I multiply root over 2 by n with root over 1 by 2, then it becomes root over 1 by n, and for other rows, these are root over 2 by n. So, with this n point density transformation matrix representation, we can express the transformation of an input vector of length n, and you remember that we are using the column vector notation. So, if I multiply an n cross n matrix with an n cross 1 column vector, you will get a transformation matrix whose dimension would be also n cross 1. That means you get the same length transformation matrix. So, these are the coefficients of the discrete cosine transforms. So, some of the properties of type 2 DCT that we can prove, and here I will simply state them. One of the property is that if we look at the rows of the discrete cosine transform, they are either symmetric, that means they are even row, and then or antisymmetric, and it alternates. So, even if we consider the first row, as you see that the k is 0, which means the value would be all these terms with the setting with the k equal to 0, this is equal to 1 because cos of 0 is 1. So, all the values would be root over 1 by n. That is the first row, elements of the first row. It is a symmetric. Symmetric means if I consider a row, say if I write 1 by say root 2, let me write 1 by root 4 where n is 4, 1 by root 4, 1 by root 4, 1 by root 4. That is the first row. So, symmetric is that at the center point, if I take the half of the array position, the center position of the array, then both sides will have a symmetry. That is event symmetry, the way we understand the event symmetry. Whereas the second row, again the alternate rows, they are antisymmetric, which means in some cases it could be, for example, for 4-point DCT, if I put k equal to 4, so the value would be cos, if I write it in this way, that for k equal to 2, the value would be root over 2 by 4, that is a 4-point DCT. So, n equal to 4, then cos of pi 2. So, I am writing the value of rho of Cn for k equal to 2. That means k equal to 1. Let me write for k equal to 1. So, it would be root over 2 by 4 cos of pi, then 2n plus 1 divided by 2 into 4. Okay. So, these are the elements for n starting from 0 to 3. So, for k, this is a k equal to 1, that row can be described, only n would be varying, which means that root over half cos of, so first n equal to 0, so this is 2 cross 4, this is pi by 8, then let me take out root over, or let me write also, no, only few elements, then root over half cos of pi, it would be n equal to 1. So, 3 pi by 8 cos of 5 pi by 8 cos of 7 pi by 8. So, in this case we can see that cos pi by 8 and this becomes cos of pi minus pi by 8, and as you know cos of pi minus theta is equal to minus cos theta. So, we can find out that cos of pi minus theta is equal to minus cos theta, right. So, we will be, so that means it is basically 1 by root 2 of minus cos of pi by 8. Similarly, cos of 5 pi by 8 is once again cos of pi minus 3 pi by 8, which is also negation of this. So, that is why this will be minus of this and minus of 3 pi by 8 and minus of pi by 8. These elements are negative. So, it becomes antisymmetric. This is odd row, and it goes like this. That is what is written here. you can see that for k equal to even, it is even row. So, that means k value 0, 2 like this, and for k equal to odd, it is antisymmetric, and it shows, this property shows that. Another thing is that this matrix is an orthonormal matrix. So, being an orthonormal matrix, you can compute its inverse very easily. So, if I take the transpose of Cn, so this T is transpose of a matrix, and inverse of this transformation matrix is simply its transpose of the matrix. So, if I want to compute the origin input vector from its transformation big X, this is the transformation matrix, this is the transform vector, this is the input vector. So, I can write it as Cn inverse X, which is equal to Cn transpose of X. So, the computation of inverse becomes simplified. Now, one of the property in the transform space that is very often used for image operations, that is convolution multiplication property. I have mentioned this property while our discussion on convolutions during fundamentals, while discussing the fundamentals of image operations. So, once again, let us revisit this concept. So, you know that convolution operation in the continuous domain, this can be represented by this operation f tau h t minus tau d tau integrations from the whole domain. So, this is how the continuous domain representation is there, and basically it's a linear time invariant system for which you get, or linear shift invariant system if you generalize the variables domain. So, shift in time, then we say time invariant, but it could be any other variable like spatial domain variation. So, there we call shift invariant. So there this property holds. So, when this convolution property holds, then we can apply the respective multiplication property by exploiting the property of the Fourier transform. It can be proved from the Fourier transform. So, if I consider the Fourier transform of this function, this is also a function of t. So, Fourier transform of this function, which is f j omega, which we write f j omega. Fourier transform of this function, which we write, say, this, if this is y t, this is equal to y t. So, let me write it as y j omega. Now, this y j omega can be computed from Fourier transform of the input signal, that is f t input function, and also Fourier transform of the impulse response, that is, say, corresponding to function h t, we have Fourier transform h j omega. So, if I multiply them, then that should be same as the Fourier transform of the output of the convolution operation. So, this is the convolution multiplication property, and this property holds in Fourier transform domain. So, let us see how this property is applicable for discrete domain. Now, the convolution operations, equivalent convolution operations in discrete domain can be described in this form, when particularly we consider you have an infinite sequence. So, your sequence is infinite. As you can see here, suppose I take some train of sequence just to explain, and this is once again the linear shift invariant property, and suppose this Hn, just for simplicity let me show it like this, it is a discretized version of this Hn. So, what happens when you apply this convolution operations on that? So, the corresponding to this impulse, it will generate an impulse like this. So, it is a causal system, if I consider it is a causal system. So, this is the starting point synchronized. So, this is the, say, 0th point. So, it will generate this impulse here, and Then for this one, once again, say this is the point, it will be scaled version of this depending upon the magnitude, and say this one, the scale version of this. Finally, the summation of all these values. So these are to be summed up. So you will get some summed up values, and finally you will get a profile like this as an output, and that is what is expressed here. You can consider that your impulse response is shifted at every point. This is Hn minus m, and then multiplied by the corresponding functional value at mth point, and then the aggregation of them, accumulation of them is giving you the linear transformation, linear output of the system. Now, in the discrete domain, instead of linear transformations, because we are handling finite sequences, so another one kind of convolution is very relevant. We call it periodic convolution, which means we convolve only with the signals restricted to one period only. So it can be shown that if the period of both the input signal, input sequence, and also the impulse response, sequence or the impulse response, if those periods are same, or any two finite sequences whose periods are same, it will also produce with this convolution operation, the linear convolution. If I apply linear convolution, so if you have periodic signal, you can extend it to infinity. You can stretch it to infinity, and if I go on applying them with this equation, which it is equivalent, we also observe the same periodicity in the output. So which means that now if I have certain signal like this, say it is a periodic signal, and let us consider that is also discretized, and also another convolution, another impulse response which may look like this, say that means a impulse response which is also periodic. Then you will also get some response, maybe something like that, and which will be also of the same period. If this period is, but they are to be of same period. Suppose this is the period n, and this is also of period n, and this is also of period. Now, if they are not of same period, then this property does not hold. That is, I mean, then you won't get the periodic output. So the advantage here that, so you can define convolution using only the finite sequence related to the one period, and from there you can compute the periodicity, and that kind of convolution, so it is sufficient to compute only n values. It is sufficient to compute only n consecutive values that will define you the period. So this kind of convolution is called circular convolutions, because you are if I consider any particular point, if I consider any particular input at any time point, say n equal to m, so we would take Fm, and then around, and from there we take the impulse response. So Fm will produce an impulse response. Similarly, m minus, this Fm also has an similarly, say m minus 1 input also it will produce another one, but once suppose m is equal to n, so next input should be considered as, if say m equal to n, so next input should be considered as f0, and for that you have another impulse response, and it will proceed, and finally the overall ensemble would be a periodic signal of length n. So how do you compute these periodic convolutions? how we are computing in that case periodic signal, periodic convolution, let us see that. That is a circular convolution. So, the expression would be as I was mentioning that if I consider the same expression, I will be only computing for n points. That means, I will be computing for n points of output and n varying from 0 to n minus 1, because they are of the same period, and it is the same linear convolution expression that I am expressing here. So, there if I use the respective definitions only at the positive part, then you can see that Fm into Hn minus 1, I am taking the summation till nth point, because till nth point at m equal to n, this H, this becomes at m equal to n, this becomes H0. So, till that the definition of my impulse response is valid, because I have defined impulse response only for positive m, only for positive side, positive argument. But moment it becomes n is greater than m is greater than n. So, for example, say m is n plus 1, right, m is n plus 1. So, it becomes h minus 1. So, the definition for the h minus 1, we apply this periodic definition. You just apply in the periodic function, as you know that a function is periodic if Fm is equals Fm plus n, where n is the length of the period. Similarly, we are just adding plus n, then this part, even after putting m equal to n plus 1, if it is minus 1, if I add plus 1, it becomes n minus 1. So, it is again defined, it becomes a positive number, and this definition of the sequence Hn, the given sequence, is valid there. So, functional definition remains intact. So, this is simply that this is the trick that we are using in this expression, because as we go on increasing m, these values now will be decreasing from n minus 1 towards the value n. And this is how this convolution equivalent computation looks like this, and this is called circular convolution. So, this expression called circular convolution. Now, the interesting part is that the convolution multiplication property for circular convolution holds for the discrete Fourier transform. That means, if I take the discrete Fourier transform of this function, which is actually discrete Fourier transform of this function, by applying the linear and distributive rule of the discrete Fourier transform, you can show that this is equivalent to the multiplication of discrete Fourier transform of the input sequence and also the impulse response. So, note that they are of same length. So, in discrete Fourier transform, they are n point discrete Fourier transform. So, the CMP or convolution multiplication property for DFT holds for circular convolution. And in a short notation, we have written in this form, you may note that this operator I am using to denote it's a discrete Fourier transform of a sequence. So, if the sequence is Fn, then this hat, f hat of that sequence, f hat operation denotes its discrete Fourier transform, just for the notational convenience. So, the multiplication of two discrete Fourier transforms, one for the input sequence, another for the sequence for the impulse response, becomes the discrete Fourier transform of the circularly convolved sequence of these two sequences. Similar to periodic extension of signal, we discussed also anti-periodic extension of signals. Now, here also it is observed that if we make anti-periodic extension of both input and output by the same length of anti-periodicity, then your convolved output would be also anti-periodic of the same length. Now, you note that anti-periodic antiperiodic signal means also it is a periodic signal. It is the length of the period is twice of the length of the antiperiod. That we have discussed earlier. So, suppose it is an antiperiodic function with an antiperiod n, and say this is the property for antiperiodicity, that if x plus n equals minus fx. So, if we have a signal, I have earlier also have mentioned that say these are the sequence, and then if say the antiperiodicity say n equal to 3, then n equal to 4 would be for the fourth point would be minus of this. I have shown it slightly elongated here, it should be little shorter. Then so it would be negative of all these samples. Once again, next again it will be positive. So you see that it is actually it is a periodic signal, because this is the period. So the twice of that period becomes the twice of that length of antiperiod becomes the length of the period. So as I mentioned, it is a periodic function of period twice n, and for the antiperiodic signal, the convolution what we can apply, I mean the linear convolution, if I extend it to antiperiodic signals, then that convolutions can be expressed in the form of skew circular convolution, because here also it is sufficient to compute only the functional values corresponding to one antiperiod, only those n samples, because rest of the sequence, rest of the points of the sequence are well defined. So, here as I mentioned that you have the same antiperiod in the output if we have same length of antiperiodic signals for two signals, the convolution between them will produce the same length of antiperiod for the output. So, when I express a skew circular convolution, if I compute this quantity and apply the antiperiodic extension property, now you can see that this sign becomes negative, because h n minus m plus n is minus of h n minus m. So, this is basically minus of h n minus m. So, that is why this minus sign came, because h n minus m is defined in your sequence. So, this is how this expression, this is equivalent expression. So, for antiperiodic for the skew circular convolution, convolution multiplication property once again holds in this form, that we can see for some of the transformations convolution multiplication property holds for skew circular convolution. So, let me elaborate this part. So, for some DCTs and also DSTs, circular convolution for circular convolution multiplication property holds, like type 2 DCT is one example. Similarly, for some DCTs and DSTs, skew circular convolution property holds. So, this is one property, and this property, this holding of this property is also little tricky. It is not that same transformation is used for both the cases. Now, when we are considering type 1 DCT properties, their convolution multiplication property of type 1 DCT for both the functions xn and hn, that means input and also the response, that is the way we understand it. Now, that is equivalent to circular convolution of both of them, and that too also the result would be also in type 1 DCT. But take look at this one. Here actually convolution multiplication property holds in a different form. you take type 2 density of one of them, say xn, and take type 1 density of the other one, say hn. You should note that their period should be same for the density. That means, as I mentioned, that you choose such a length of signal that their period, both of their period remains same, say capital N, say twice n. And then for that, the output will be the type 2 density of the convolved output. So you have the type 2 density of input and type 2 density of output, whereas your impulse response, it has to be transformed into type 1 density. So these are some interesting feature, because we can apply it for designing filters in density domain. We can compute directly in type 2 density domain, because filter response is a kind of specification. So whether you specify as a sequence Hn or whether you specify as a sequence of its type 1 density, it is almost same. So it is an one-time job. So once you specify it, then given any arbitrary input, I should compute type 2 density of that input and multiply with that given type 1 density of that impulse response sequence. And of course, there is a scale factor, as you can see, it is also there. Then you will get the type 2 density. So this is type 2 density of the output. So output is also in the type 2 density form. This is an example where skew circular convolution is applicable in the convolution multiplication property, but that is in the type 3 density domain. And here also you see that everything in type 3 density. You have input in type 3 density, you have the impulse response in type 3 density, then the skew circular convolution of these two sequences, if you compute, the type 3 density of that convolved output would be the same as it is. The scale factor, please note. So these are certain convolution multiplication properties of in the transform space, which has its use in some applications. We will be discussing later how these properties are being used for particularly developing filters in the type 2 density domain. Now, so far I have discussed about one-dimensional transforms. Now, let us extend this discussion. Let us consider their extensions in 2 dimension. And as I have mentioned earlier also, that in 2-dimensional form, we want a transformation of 2 dimension means that it is an expansion, linear expansions of 2-dimensional basis functions. Now, when we consider this in the continuous space, now this expansion becomes easily extendable if I consider a 2-dimensional basis function is derived from its 1-dimensional forms, which means that there is a class of separable functions. So each dimension, like here x and y, they have two basis functions. So their basis functions can be factorized. One only the function of x, another one is only the function of y. So if I can express the 2-dimensional function in terms of two factors of these 2 1-dimensional functions of each dimension separately, then it is a separable function. Now, if this basis functions in 1 dimension is orthogonal, then it can be easily shown for this kind of set of separable functions in 2D, they are also orthogonal. So that is how your orthogonal expansion becomes once again convenient and specification. So all the basis functions, whatever we have discussed in 1-dimensional transforms, those are easily extended by considering simply they are extended from as a product of those 2 different functions of two variables. So this is how we can consider them. So if B is orthogonal and complete in 1 dimension, similarly in 2 dimension, that means G is so. I mean, if G is complete and orthogonal, then B is so. So it reuses 1-dimensional transform. That means we can compute like this. Say if you observe that this one is computing the inner product of the function fxy by keeping y as a constant. So, if I keep y constant, it becomes an one dimensional signal. So, it is an inner product of them, and whatever transforms you get. So, at every y, at every value of y, you get these transforms. Again, that becomes a function of y. So, now this is inner product of this transformed function where of variable y. So, it is inner product of these two. So, the same computation, because it is the same type of computations you are applying, and if I develop a module for computing one dimensional transform, same module can be repeated here in this case. So, in the 2D discrete form, how it is useful, we will be discussing this. You should note here that though we have used similar symbols, but they could be of completely two different sets. They may not be of the same sets. So, in 2D discrete transform also, we use this separability part notation. So, what we do there, as I mentioned, that you have the transformation of the column vectors. So, if you consider a input matrix, if you consider input matrix like a two dimensional arrangement of your input, so you may consider each column of that matrix is a vector. Say this is say x0, this is x1, like this. This is say xn minus 1. And suppose you have a transformation matrix A. That is a one dimensional transformation matrix, which means in this case say n cross n. Say this is of length. Let us assume these are of length n, and also there are we may say there are m number of vectors, say m number of vectors. Now, what you are doing, you are multiplying each matrix with each column vector. So, you are multiplying them and then you are transforming them. So, when you are multiplying them, so this is your y0, this is say y1. So, which means that you are multiplying this matrix with this column vector and you produce y0. Multiply this with this column vector, you produce y1, and it goes up to say ym minus 1. There are m minus 1. So, you have transformed all these columns. Now, as you know that this is the dimension. So, along these dimensions you have transformed. For 2 dimension, what you now you have to do along these dimensions for this transformation. So, I have to multiply this. Now, rows would be my vectors. So, instead of since I have to convert it into a column form, so what I will do, I will make a transpose operation of this matrix. So, I will take the transpose operation and then all these columns. So, these columns becomes my row. So, this is my row, this is the y0, so this is my next row, this is y1, and this is say this is ym minus 1. So, now what you have with you? So, now you can see that when you are multiplying, so now your columns, all these columns, these are the length, and what is this length? This length is of length m, okay. So, this is of length m, so this length is of m, because these are m rows and this length is n. So, here you require the transformation matrix corresponding to m point transformation. So, a transformation matrix of A m cross m, and there you are multiplying it. So, you multiply them. So, let me consider this column. So, this becomes this one. Say, let me consider this is Z0, then for this column it is Z1 like this, and in this way it goes and it goes till, since there are n columns, these are all of length L, so this is Zn. So this dimension is m and there are n columns. Now when you get it, naturally you get it in the form of a you get it in the form of a two-dimensional in the transposed form, because you have transposed it and then you have multiplied it. So again you perform a transpose operation to rearrange them so that your transformation rows becomes rows. So this column become row, and in this way finally this is your transformation, two-dimensional transformation, and that is how this this modularity consideration is going on. So we, as I was mentioning, that first you transform columns. So this I was discussing, this is a transformation of columns. Then you transform rows, that means I have to transform these rows, but I will do it in this way, I will transpose and do it. So this is defined, this computation, what I have schematically shown in the mathematical form, let me explain now. So you have an input matrix X m cross n, as I was mentioning. So you have an m cross n matrix, which means in this case your number of rows is m. So the length of column is m and you have n columns, small n columns. So when you perform the column-wise transformation, you take a transformation matrix corresponding to m. I have mentioned for n point dct. So you have to take m point transformation. So if it is a dct transformation, you take m point dct transformation, which is generally denoted by b here, and you get a transformation y1, resultant transformation y1. So now its rows are to be transformed, and then you apply n point transformation, and overall you apply the transpose operation. That is what I discussed just a few seconds before. So if I take these operation, if I simplify these steps, as you know that if I take transpose of product of two matrices, it is basically product of transposes of those matrices in this reverse order. So this can be written in this way. Y1 transpose becomes Y1, and this is B n cross n transpose. So now if I just replace Y1 by this value, this will be my expression. So it looks like a quadratic operation, but actually you see that stepwise it's linear operations. You are applying twice these operations. So this is the transformation. So this is the two-dimensional input, and these are the transformation matrices which are corresponding to one-dimensional transformation matrix. So one is pre-multiplied, another one is post-multiplied. This transpose is post-multiplied. So this is the result. So now I will be extending this discussion. So for discrete Fourier transform, we know that in the transform domain, in the one dimension, you have the basis function. This is a complex conjugate of basis function of one dimension. So you just factor of these two. I mean, this product of these two will form the 2D basis functions, and you apply it and you form it, and then this is the expansion, again the same expansion 2D form. But when we express in the matrix form, then this transformation matrix is simply the DFT transformation matrix of m point DFT transformation matrix, and this is the n point DFT transformation matrix. This is transpose of that one itself. So the final transformation can be written. So this f denotes the two-dimensional array of the input of size m cross n. Here you should note this m I should have written capital M, okay, because I have taken m point here. So property of separability is used here, and this is how the property of separability can be also used. And there are first Fourier transforms which I have not discussed here, but you can read advanced signal processing book or any signal processing book. You will get this algorithm. So, you see that this computation is just Fourier transform in one domain. So, you can apply first Fourier transform for this module, and for the next part also you can apply first Fourier transforms. So, one examples of DFT just for visualization I have shown. So, this is the input image and its corresponding transformations will give you one real part, another imaginary part, and we can express in terms of magnitude and phase. But no, we are showing the centering the frequency at the center of the at the center point of the image, and that is how we are displaying. So, shifting the origin at the center of the image, that is what we are displaying here. So, this is just one, and there are certain symmetry you may observe in this picture also, as it is now observed for the property of the Fourier transform. In two-dimensional DCT, similar expressions could be obtained. Like here, we consider the corresponding basis functions. These are the corresponding basis functions, and this is for the thing. These are alpha k into alpha l. Need to check that, and so this should not be like this, because it's the product of these two functions, right? So this square should not be there. And so these are the, as you can see, these basis functions are simply product of two one-dimensional basis functions. Their variables are scope variables are different because they are separable functions. So in the matrix representation, once again, these transformations can be written in this form. So if I have this type 2 DCT transformation matrix, as I mentioned just in the beginning of this lecture, this is the notation. So, it is an m point type 2 DCT, this is an n point type 2 DCT, and your array is m cross n array. And then you get your DCT matrix, that is DCT coefficients, as an array of m cross n. So, this is the example of discrete cosine transform. Here the advantage is that you can just simply use the real values of the transformations. There is no imaginary part. So, you have only to show, you can show it by one component only. And there are 16 different types of DCTs and DSTs, as I mentioned. So, the next topic or next part of our transformations, image transforms, that we are going to discuss, those are of wavelets. Now, wavelets are functions which have ideally finite support in both its original domain, that is in time or space, and also in the transform domain, that is in the frequency space. So, here usually, as you see that the basis functions what we have considered, the basis functions itself, they have certain properties both in time and also frequency space. But in wavelets, we consider those basis functions should have some finite support in both time and frequency. We'll understand. We'll discuss that. What does it mean? Actually, no such ideal function exists where you will have a very small support both in time and frequency. So either you have a very narrow support in time, then your frequency domain support gets wider, or you have a very narrow support in frequency, then your time domain support becomes wider. But there is a trade-off for certain functions. Those we will be considering candidates for wavelet transforms. So, we attempt to match these properties as far as possible. And these are acting like a basis function. So, the idea here is that, say, if you have a wavelet, so as I said, let us give an example. Say this is a function which has a very finite and small support, say in the time domain. This is a time domain function. Okay, so it's a finite time. So if I get a get any function, any arbitrary function. So, at every point what I can do, I can consider a translated form of this function and take the inner product, of this part, because outside this zone it will be 0. So, if the accumulated product of these two functions, whatever you get, now that would give me a coefficient. Now, you translate this one over the space and you get this coefficient. So, this is a kind of transform description. So, when I am trying to reconstruct the function, as if those linear combinations of those translated basis functions should give me some approximation of my original function. Now, it depends upon, of course, the property of these basis functions, because as you understand that it is what we are computing is inner product at every point, then you are accumulating them. So, they are if I take the linear combinations, it is not going to give me exactly the same function back. But there are certain wavelet functions where you can get this kind of properties, and those wavelet functions can be used for orthogonal expansion. So, those are the orthogonal basis functions of the wavelet. There are certain wavelets, but not necessarily wavelet has to be orthogonal. It is a kind of redundant description, and there are ways to recover the full signal with that representation, which is not simple summation of this linear expansions or linear combinations of these wavelets. So, wavelet has one of the good property of wavelet is that it has a good localization property in both time and frequency domain. Some of the examples for wavelets, say we consider the Dirac delta function. Now, it is an impulse response. As you can see, it is infinitely small interval, almost 0, right. So, it is a very narrow support, very precise support at t equal to 0, and outside it is 0. So, it is an infinity, but if you take integration, then this become equal to 1. So, it is impulse is infinite, but total power, total amount of area under that impulse should be equal to 1. So, that is the interesting part. But if I take the frequency domain representation or transform of this Fourier transform of these Dirac delta functions, you know that it will give us a uniform, it will give this kind of function, a constant function over frequency. So, this is how the Dirac delta functions in the range, it will give that. Or if I consider a sinusoid in the time domain, and we know that representation of sinusoid in the frequency domain is just for that component which is like an impulse, because both imaginary components would be there. So, at 4 and minus 4, like so, these are the frequency I am considering the representation, say f equal to twice pi f equal to omega. So, you get this kind of representation. So, this is the other example. So, you can see that for this wavelet function, you have both the domains, it is not in both the domains this finite narrow support is not possible. These are two extreme cases, of course. Now, there are certain functions where you have this kind of I should say roughly this kind of similar similar type of supports, similar width of supports of same order of supports. Those are our candidates here. So, one of the function is again the Gaussian function, which is we know this function in various cases in various various applications, the same function Gaussian function. So, if you look at this Gaussian function, so suppose this function is expressed in this form, you can see that here sigma is the width of this effective width. So, this is say 2 sigma, twice sigma, this is effective width of the Gaussian function. We know this is the parameter and centering at t equal to 0. If I take the Fourier transform of this Gaussian function, then its transform also has a Gaussian shape, but now the width, this width, if I take this width is inversely proportional. You can see that what is this width here. So, I can write it if I just ignore this normalization part. So, this could be written as omega square 2 by sigma square, which means I have this width, it's 2 by sigma. Okay. So, this width looks like a 2 by sigma. Okay. So, earlier it was 2 sigma, this is 2 by sigma. So, it is inversely proportional. So, though no, they are of same shape, but no, if one support is narrow, other support gets wider. And one of the interesting, this fact can be expressed also in from the mathematical constraint. There is a mathematical constraint which is similar to what we observed in physics, quantum physics, as an Heisenberg's uncertainty principle, when we want to measure the momentum and the position, both momentum and positions, if we want to measure. Now, the product of that, there would be always an uncertainty. So, there is an uncertainty regarding that. So, if you consider the product of these two, sigma t square and sigma f square, you will always you will find that it has to be greater than equal 1 by 4. You take any signal and you consider this sigma is, as you know, it is related to the standard deviation of these distributions. So, this sigma t and sigma f, they are defined as the standard deviation. So, variance of t weighted by g squared t, and similar for f, for any function it holds. And this is called the uncertainty principle in the wavelet domain, akin to the Heisenberg's uncertainty principle. So, today let me stop here, and we will continue this discussion on wavelet transform for the next lecture. Thank you very much for your listening.